I'm Lindsay Lewis, editor of Building Enclosure. Thanks for listening along with us today. Wells Fargo has opened the largest net positive corporate campus ever built in the U.S., generating more energy on site than it consumes. The world-class 850,000 square foot campus employs cutting-edge sustainable design, including 360,000 square feet of solar panels, low-carbon concrete, dynamic glazing, and a high-performance envelope. Designed by Corgan, the innovative campus in Irving, Texas, is home to more than 4,000 employees. Varun Kohli, Principal and Director of Sustainability at Corgan, and Matt McDonald, Principal and Office Sector Leader at Corgan, are here today to join me in discussing the project. Varun and Matt, thanks for sitting with me.
Good to be here. Thanks for having us.
Thanks for having us.
We're an architectural and interior design firm headquartered here in North Texas. We've got 21 offices across the country, and we've got about 1,200 employees that have all been a part of this and seen this. So we're excited to get to showcase and talk a little bit about what we've done here today.
Yeah, thank you for joining me. So back to the project. The campus is the largest net positive corporate facility ever built in the U.S., correct?
That is correct. As far as we know, we don't see any official tracking on that, but as far as we know, that's the case. Yes.
I can tell you, Lindsay, it's certainly been designed for net positive energy. And we have checked with the ILFI team that usually certifies all of the net zero projects. And the largest we have seen so far is in the range of 200 to 300,000 square feet. So this is by far a very large project.
Yeah. Now, with that being said, what was the most significant architectural decisions that enabled net positive performance at this scale?
Bottom line, it was what was the power source going to be? And when you're looking at sustainability and creating energy on site, the obvious choice in Texas is to look at solar. So as you said in the intro, we're 360,000 square feet all on one level. That's a good amount of space. And so figuring out how to incorporate that, one, quantifying it to make sure we had enough space on site to get the amount of space we needed to generate that kind of power, and then how we incorporate that into the architecture of the buildings and get it to where it is appropriately manifested in the architecture itself, but also complying with zoning and city regulations to make sure it was pleasing and acceptable to everybody.
If I may add, I think one of the key things here is also reduction, right? Like we can generate a lot of energy on site. You know, we had the advantage of having all that roof surface to put out the solar panels, but the first step is really to reduce the energy use. And that's where the building envelope, the building massing, orientation, the facade articulation, all of those design impacts actually help reduce the energy. The EUI was down to close to around 36 kBTU per square foot per year. So that's a really good number. And then we were able to generate all that energy. So there was a lot of effort that went into reducing the energy first.
Now, speaking on that early energy modeling, how did that modeling, the solar analysis, and site evaluation influence the massing, orientation, and program distribution of the campus?
Matt?
The energy model, so it was driving, a lot of it was by the EUI, and we were trying to quantify how many individuals on the campus, quantifying it right down to the plug loads of each of their desk worktop units, what was going to be plugged into power on a daily basis. So we literally got really, really into the details on how much power each particular individual was using on a daily basis. And when you overlay that with shift work, you've got the bulk of the population is there from 8 to 5 or therewith, but it's also a 24-7 operation. So there were employees and those kind of things that were working and using the facility after hours. So averaging all that out and calculating that out helped us and hurt us depending on the time of usage. But we got to that level of detail to really make sure we were quantifying and getting the energy calculations just right.
I can add, you know, our team did get lucky in terms of like the orientation of the building. The building's orientation is the larger facades are facing north and south. That helped us reduce the energy loads, the solar loads. Also, that orientation allowed us to get maximized views towards this water body that exists within the district. So it was kind of a double win for us in that way. But that orientation, along with the articulation, the shading elements, the high performance envelope, all of those things were studied early on and made sure that helped reduce the energy consumption in the building. So I would say, there's definitely, and couple that with the fact that we were looking at daylighting inside. So it's really a balance of trying to mitigate the solar heat gains, but at the same time ensuring that we're getting enough natural light, because as you may know, in office buildings, lighting loads are huge. So we had to make sure that we were balancing that out and making sure that the lighting loads were reduced while we were reducing the solar heat gains.
I was reading a little bit about the project's high performance enclosure between the glazing that was used and the low carbon concrete. So my question is, what envelope strategies had the largest impact on reducing energy demand, especially in a hotter climate like Texas?
There were a couple of things. So typical office buildings, you see a lot of them that are all glass buildings. So one of the things that we really tried not to do here is to really minimize and balance the amount of glazing to opaque ratio. So we worked really hard on the articulation of the facade to make sure we were getting, as Varun said, both natural light, getting accessible views to the outdoors, and in balancing that light to opacity ratio on the facade to maintain efficiency, but yet maintain energy efficiency as well. The other thing that we did is the glazing itself is electrochromic glass. So it tints over the course of the day, depending on timing and solar exposure and those kind of things. So there are no mini blinds anywhere in the building. Every piece of glazing is fully visible at all times. However, it tints based on the amount of solar exposure it's gaining. So on the north facade, you get a pretty nice evenly lit facade throughout most of the day. On the southern facade, it does darken, and it does make to help screen some of that sun. So you're reducing glare. You are still maintaining natural light, but you're not getting that intense glare on computer screens, and the overall experience is really quite pleasant.
Yeah, the U value of the glazing is like 0.178, which is a pretty high performance value. The opaque components also have pretty good U values. I think it's close to 0.077. So it's a really tight, good envelope. And I think just to add to that electrochromic glazing, that technology has advanced quite a bit in the past few years. So if you look at some of the older generations, you can kind of see these patchy modes, or the gradation is not as even, or the color quality of light is not as good. But here with the new generation, the new technology, actually the quality of light inside, even after it darkens, it's pretty even. It's very natural. It works a lot better than what we've seen in the past.
Going back to the solar that was used, how did the design team integrate such an expansive PV array into the architectural language of the campus without compromising, say, aesthetics?
So one of the things we have to recognize here is in Texas, we are still very vehicular focused. Everyone still drives their own cars to and from work, those types of things. So in a suburban campus like this, we do have significant parking structures that accommodate those cars. So you've got 4,000 people coming in and out of that garage at different times of the day throughout the day. Not only does it help consolidate the footprint of service parking, but it does provide a large surface on the top floor. If you look at almost any parking structure, it's rarely used. It's high up there. You're not really getting the benefit of the shading, so it's not used all that much. So what we're able to do is utilize the roofs of each of the office buildings, as well as the roof of the parking structure itself, to get the significant amount of square footage we need on the buildings and integrate them into the building, so they're not standalone in some big solar field or anything like that. As part of the campus, they are literally integrated into the building architecture. So both office towers have a complete array across the top, over above all the roof and all the mechanical equipment. And the top level of the parking structure is also fully covered. So it gives you the appropriate amount of the 360,000 square foot of area you need to accommodate and generate that kind of power. But it also provides some added benefit of higher use and able to diversify the parking. People are spreading out the parking throughout the garage, and it made that whole thing efficient. So there were a lot of indirect benefits of how that was implemented. And it gave us the area we needed to generate that kind of power.
Another added benefit is that when these canopies, and these are elevated about 20, 25 feet, correct me if I'm wrong, Matt, but it's a really like when you are on that roof, it's an amazing space underneath that canopy. It's quite surprisingly nice. And one other added benefit is when they're shading all these cooling towers that are sitting on top of the roof, the efficiency actually goes up because you're not exposing all that, mechanical equipment and cooling towers to direct solar heat gains. So there's another advantage of doing that.
You both already touched on this, but I was wondering if you wanted to expand maybe a bit. In hotter climates like in Irving, Texas, what passive and active design strategies were essential in controlling the heat gain while still maximizing those daylighting and the views?
I think, we lean quite a bit on the technology, the electrochromic glazing for sure. But, some of the points that Matt just made, making sure that we're not simply, blindly going and designing 100%, glazed building. Here, the window-wall ratio is close to 60% or less, depending on the orientation. So there was a lot of thought put into like how much glazing do we need, and if you notice the design itself with vertical portions rather than horizontally cutting off. So there are areas of the building where you can actually get the views, enjoy the full floor-to-ceiling glazing, yet reduce the window-wall ratio. I think that's really key. Sometimes we often think that it takes a lot more to get to a much more higher performance building. Sometimes it's just smaller, good design decisions that you make early on, right? And that's what happened here is that you're reducing the window wall ratio, making sure that we have good U values, making sure that our glazing has really high SHGC. In this case, being dynamic, the SHGC value changes as the glazing changes. So I think that really helped us a lot. One other thing I think Matt pointed to, but I thought was really amazing is the fact that we were working so closely with the client and understanding the schedules, right? So there's two buildings, and if you kind of just scatter all your teams across two buildings, you might get a completely, mismatched schedule, right? You might have people who are working 18, 24 hours a day in a portion of a building and then also in another portion of the building. So we actually worked with the clients to make sure that all of that was aligned so that one building had similar occupancy schedules, which was maybe 18 hours, 24 hours, versus another building that had much less. And that allows us operationally for the clients to actually turn down or, turn off potentially portions of the building and really save energy. So that is, again, a small piece. There's no silver bullet, right? Like you have to use everything possible to reduce the energy from the design side, from the operational side, and all of it sort of comes together in this design.
Lastly, I do want to ask, how did low carbon concrete and other material choices factor into life cycle carbon analysis and the long-term sustainability goals for this project?
So we use the low carbon concrete on the structure exclusively. So in Texas, not a lot of steel production. So the concrete structure, the building itself is made of concrete floors and columns. So that gave us a tremendous opportunity to utilize the low carbon concrete at a large scale and help present and help, develop the structure or the entire overall calculation around that, because there's so much concrete on the site, both in the structure, and then we've got other concrete that we did use some of the low carbon in the precast panels themselves. So those two elements themselves help us attain a very responsible and sustainable approach to the structure, which is not, concrete is not always known for that. And so to be able to layer that into this was really kind of an added benefit. Varun, anything you want to add to that?
Yeah, no, I can say we got about 16% reduction in GWP just by, replacing some of the concrete with low carbon concrete. We would have gone farther, but there's always concerns in making sure that there was a good balance between aesthetics, structural requirements and things of that nature. But 16% is still a good reduction in the GWP value.
Well, thank you both again for your time today.
Thank you. Pleasure to be here.
If anyone listening has any questions, please feel free to reach out to myself or Corgan, and we'd love to continue the conversation. Until next time, visit us on buildingenclosureonline.com for your technical and educational resources.